Hello students, in this topic we are going to see simple harmonic motion and waves. So first we will discuss about the simple harmonic motion. In that we are just going to cover what do you mean by that simple harmonic motion. Then you can say that, so the comparison between periodic motion and oscillatory motion, then what is that differential equations, then the equations related to the acceleration, velocity, displacement, how you can say that convert the uniform circular motion into a simple harmonic motion, then how we are going to represent that velocity, acceleration and again displacement with the help of graphs, then the energy, that is the kinetic energy and potential energy in case of your SHM. Then after that we will see the free and damped oscillations in the case of your this SHM. So let's start with the first one. So when I'm saying that the periodic motion, so just I'm considering that your simple harmonic motion is nothing but your periodic motion. So that periodic motion, that object is going to perform the same motion after a definite interval of time. That motion we are going to call it as a periodic motion. So let's say for example the motion of this simple pendulum. Again we know that the motion of your earth around that definitely the sun. So again you can say that the cyclist who is performing the motion along a circular track. So again the motion of your hand clock, that minute hand, hour hand, all of them are just doing that your periodic motion. So that is what we can call, they are just repeating the same set of your movement again and again. That is what we will call it as a periodic motion. So it is having some definite time, again it is having some amplitude also. So that what we called it as a periodic motion. So now if we just talk about the oscillatory motion. So the oscillatory motion, it is a kind of, you can say that the to and fro motion. So it is just, you can show that back and forth motion, the motion of this block which is connected to this spring. So you can see that, so it is just performing that to and fro motion. So that is what we will call it as a oscillatory. So this is nothing but the oscillatory motion. Now obviously it is a periodic motion, so taking place to and fro or back and forth about a fixed point is called as a oscillatory motion. So the motion of simple pendulum or the motion of your loaded spring that we have seen. So this is nothing but again the simple pendulum which we have shown over here. So this is also, we can call it as a oscillatory motion. So this is again the to and fro motion. So this is what we call it as a oscillatory motion. So now the most important difference between this oscillatory motion and your periodic motion, where we can say that oscillatory motion, again it is going to repeat after a definite interval of time. So it is a periodic motion, but at the same time I can say that every periodic motion is not oscillatory. Means when I consider the example of your, let's say, earth which is revolving around the sun and it takes that 365 days to complete one revolution. So it is not back and forth or it is not to and fro motion. So it is just performing that circular motion. So by default that oscillatory motion becomes periodic motion, but every periodic motion, it is not necessary that it should be an oscillatory. So that is the most important difference between the periodic motion and oscillatory motion over here. Again, when I'm just going to call it as a harmonic oscillations or harmonic motion also. So this is also, we are going to call it as a simple harmonic motion. So now when I should call it as a harmonic, means if I can represent that motion with the help of waves, sine wave or cosine wave, then that motion I can call it as a harmonic oscillation or harmonic motion. So likewise, so the motion just we have discussed, let's say the motion of particle along this to and fro. So this is how we can say, this is just again the to and fro between these two extreme ends. For example of your simple pendulum, when I'm saying that it is just performing that your to and fro motion. So obviously it is going from the mean position towards the extreme, again getting back towards the mean, again it is going towards the extreme left and again it is coming back to the mean position. So according to that, its amplitude is also getting changed when it is going from this equilibrium to maximum towards right hand side. So we can say that its amplitude is maximum, then again it get back towards the equilibrium or mean position, it becomes 0. Again it goes to the maximum but in opposite direction, and then again it come back towards the mean position. So this motion I can represent with the help of your sine or cosine wave. So that's why it is called as a harmonic oscillations. So again, the another very interesting example, consider the block, and this block you have to connect it to the string, and observe now the motion of that block which is connected to the string. So initially there are various cases I can consider. So let's say for example where there is no extension is produced in the string. So that means I'm just going to connect that block to the string and which is placed on some surface. Yeah, okay. So now in this case the extension which is produced in the string is 0. So in the next case, let's say for example what I have to do over here. So for this particular case, let's say this is the equilibrium position where I can say the x is equals to 0. Now I'm just going to compress that spring. Now when I just compress that spring, obviously the block get displaced towards the right side. So now when I'm just going to compress this spring, you have to apply the force on the left hand side. So that's why the displacement of the block is on the left hand side, but at the same time there is one internal restoring force which will just try to oppose this external force. So that what we call it as a restoring force. So this restoring force which will act internally, and its direction is obviously opposite to that of your external force, or you can say that it is towards the mean position. So that is how we can say for this case. So where the restoring force obviously which is directed towards the right side, when the external force is on the left, the restoring force is on the right side. Again in the next case, when you just compress, one is this case, and when you stretch, yeah, in another case just try to stretch that spring. So when you just try to stretch that spring, the restoring force will act towards the mean position. So that means it will now act towards the left side. When the external force is on the right side, you're just trying to pull that your block towards the right, but the restoring force will try to restore its position, that is nothing but the equilibrium position. So that restoring force will act on the left side. Yeah, so that is how we can say. So for this particular case, so where I can say that, so the direction of external force and restoring force, they are opposite to each other, or you can say that the restoring force is always directed towards the mean position. Now we will see that simple harmonic motion, how we can represent with the help of that of your uniform circular motion as well. So we know that, so in case of your uniform circular motion, that is the motion along the circumference of circle. So if what I have to do exactly over here, so when I just consider that, so let's say this is what we can call it as a uniform circular motion. So you have to take the projection of that your particle or object on this x-axis. Yeah, so let's say it is just right now it is at point P, then just take its projection on this your x-axis. Yeah, so then you will get, yeah, so then you will find that, so when it started from this point A, so then it moves to the B. So this is how you can take the projection. Then let's say for C, take the projection, let's say again for D. So the projection, you can say that it is moving from A to D, and then again let's say D to E, and then again E to D and D to A. Yeah, so this is how actually it moves along this axis. So when it is performing this your circular motion, so at the same time you can say that after taking its projection on this axis, you will find that it is nothing but the simple harmonic motion along this axis. So that is again the to and fro motion. So that's why we can call it as nothing but your simple harmonic motion. That is also we can call it as a to and fro motion for this particular case. So let's say So let's say for example, so where I'm just considering this motion, so just take the projection over here again, yeah, over here again. So let's say again this is like that. So this is how we can say that about this your motion.